Next, we're going to talk about how to estimate the parameters of our ARIMA model using maximum likelihood estimation. So in other words, we're going to come up with phi hat 1, the estimate for phi 1. We're going to have theta hat 1 as the estimate of theta 1, and so on. Now, there's a number of different ways to estimate parameters of an ARIMA model. There's, like, for example, method of moments, unconditional least squares, conditional least squares, in addition to maximum likelihood estimation. However, maximum likelihood estimation is the best of these methods to come up with final estimates. And it's also and because it's the best, it's the most often used. Sometimes these top three methods here will be used as a way to come up with initial estimates that are used in a numerical iterative procedure to then find maximum likelihood estimates. Note that we will not be able to have nice little closed form solutions for maximum likelihood estimation with ARIMA models. We're going to have to use again these numerical iterative methods. Okay, so let me go ahead and skip ahead here. Excuse me. So to do maximum likelihood estimation, you need to define a likelihood function for your data. Overall, if you need a review of the process for maximum likelihood estimation, although it is a standard topic in all mathematical statistics courses, if you do need an introduction to it or a review of it, please take a look at my corresponding mathematical statistics course that's available on my chrismiller.com website. In that course, you will see lecture notes defining a likelihood function and all the stuff that you can do with, well, first of all, how to find a maximum likelihood estimator with a likelihood function, and also all the fun things you can do with likelihood estimators as well. Now, in my corresponding notes, I generally do not derive stuff by hand. Instead, I use a symbolic mathematical software package that automatically derives closed form solutions for maximum likelihood estimates. So please be aware of that if you do take a look at the notes. But again, at least for the kinds of models that we're going to be looking at in this course, we're not going to be able to come up with nice little closed form solutions. So I won't necessarily be able to say, well, mu hat is equal, well, let's do this. Phi hat 1 is equal to something that's a function of my data. Rather, I'm going to have to use, again, these numerical iterative methods, and I'll explain what those are coming up. Okay, so let's work with an ARMA PQ model. Here's what our model looks like. Now, to do maximum likelihood estimation, to find that likelihood function, we're going to need to have an actual distributional assumption for WT. So we're going to use the normal distribution for that. Well, I put an ARMA model here. We could just as easily work with an ARIMA model as well. The key is that basically you write your likelihood function in terms of your difference data already. And so that's why I'm just working with an ARMA model here. Now, what if, though, the expected value of t, which is mu, is not equal to 0? Notice I am using 0 there. Well, in that particular case, what you just simply do, you add this alpha parameter, which ends up being mu times 1 minus phi 1 minus all the way down to phi sub p, as we saw earlier in this course. And generally speaking, it's not good to assume that mu is equal to 0 when you're actually doing estimation. And so we will typically always have that alpha parameter in our model, unless it's a, well, in special situations we might not. Okay, so here's our model. Then written completely out. So I don't have that AR operator, I don't have that MA operator. But let's rewrite the model so that we only have WT on one side. And that's what I do here. So you have the AR part and the MA part, and then you have that alpha part there. And the reason why I rewrite my model like this is because WT is assumed to be independent from a normal distribution with mean 0 and variance sigma squared W. So that's very advantageous for us because now we have a way to write our likelihood function given our W's, which then gives us our X's as well. So our likelihood function is written in terms of what we don't know here. We don't know what the true values of phi are. So imagine, let's say, phi is a vector that has phi1 through phi p in it. We don't know theta. Again, theta is a vector for theta 1 through theta q. We don't know mu. We don't know sigma squared w. And so, given w itself, we write a likelihood function like we would normally when we have independent observations. Product from, in our case, t equal 1 to n. Here's our normal distribution that has a mean of 0. I can do some mathematical simplifications. Notice how I can bring that square root of 2 pi out. I can bring the sigma w out as well outside the product. Then I have the product of e raised to all this stuff here. Again, using properties of working with powers of quantities, I can now rewrite this as e raised to the negative sum from t equal 1 to n of wt squared over 2 sigma squared w. Okay. Now, typically with maximum likelihood estimation, you work with the natural log of the likelihood function. Let's call that natural log a script L for our notation here. Common notation that people use, a script L for this. And basically the maximum likelihood estimates, meaning that the most plausible values for our parameters given our data are the values of the phis, the thetas, mu, and sigma squared w that maximizes our likelihood function itself. The way that you find these particular values of our parameters given our data is again to use iterative numerical methods. So let's talk about one of these methods called Newton-Raphson Method. Let me just come back here. So the values of the parameters that maximize this equation are the maximum likelihood estimates. So that's how I'm going to get phi hat 1, theta hat 1, phi hat 2, and so on. Those are my MLEs. Okay. So there's a number of different numerical methods that can be used to find these maximum likelihood estimates. The quantities that maximize our likelihood function there. A very commonly used one's called the Newton-Raphson method. I'm not going to ever ask you to, like on a test, go through the details of a Newton-Raphson method by hand. Rather, my purpose here in this short segment of the notes is to show you a little bit about the process so that when we use a function in R called ARIMA, we have a general idea of how ARIMA is actually finding these maximum likelihood estimates. That's all. So, suppose we write all of our unknown parameter values into a vector. And just to make the notation easy, how about we call this vector beta, and we just simply rewrite all these parameters as beta 1 through beta k. So k is our number of parameters that we're trying to estimate. P, because we have p phis, q, because we have q thetas, and then we have a 2 here because we have sigma squared w and mu. Okay. So we're going to let then the partial of the log likelihood function for beta, that partial derivative with respect to beta sub I, meaning just one of those corresponding parameters that we're interested in. We're going to let this symbolic notation represent the first partial derivative. We can put all these first partial derivatives into a vector for beta 1 through beta k. This vector is going to be a script L, and then then in the superscript of parentheses 1, and then against a function of beta. This is commonly used notation to represent first derivatives like this, and there's obviously other notation as well. This is just the notation that I've chose. So this is a k/1 vector of these first partial derivatives. Then we can also go to the second partial derivatives as well, and what we're going to end up having is a k/k matrix. So the matrix is going to look something like this. So partial, just a second, let me write this out real quickly here. So the 1, 1 element corresponds to the partial with respect to beta 1, the second partial derivative. The 1, 2 element of this matrix as well is then represented as the partial with respect to beta 1, the partial with respect to beta 2, and I could keep on going until I get the partial with respect to beta 1, partial with respect to beta sub k. And then the second row of my matrix then again is the second partial derivative, where I take it with respect to beta 1 and beta 2. These two quantities are exactly the same. The 2, 2 element of the matrix is the second partial derivative with respect to only beta 2 itself, and so on. So when you have a matrix that looks like this, you may have heard this terminology before. This is referred to as a Hessian matrix. Okay, so given these partial derivatives, we can then do this numerical iterative procedure to find what the parameter estimates are. Without going into all the details behind how this expression comes about, simply we do as follows. Let's say in the gth iteration we come up with a particular estimate for beta hat 1. For beta hat, that whole vector of parameters. Then this estimate is found as follows. What we got for the previous iteration for beta plus an adjustment. This adjustment's based upon that Hessian matrix inverted times the vector of our first partial derivatives. So what happens then? Let's say we're at iteration 1. What we could do is as follows. Take beta hat 1 is equal to beta hat 0 plus, well, what's beta hat 0 there? That could be, for example, estimates from the method of moments, estimates that we found from the method of moments. So a way to initiate, to start this numerical iterative procedure. Plus, then we have that matrix evaluated at beta hat 0, and then we have that vector evaluated at beta hat 0 as well. So we get beta hat 1 using this matrix algebra. We have beta hat 0 already. And we look, how close is that beta hat 1 to the beta hat 0? If they're very, very close, then we stop. Our estimates are not changing. We have what's referred to as convergence. If, however, beta hat 1 is different from beta hat 0, then we do this numerical iterative procedure once again, where we take now beta hat 2 is equal to our previous estimate, beta hat 1, plus that matrix inverted evaluated at beta hat 1 times that vector evaluated at beta hat 1. Once again, we check how close is beta hat 2 to beta hat 1. If they're very, very close, then that says that this adjustment factor is not making much of an adjustment as well, and thus we have come to convergence. We have found what the parameter estimates are, and we stop. Otherwise, if beta hat 2 is different from beta hat 1, then we continue this numerical iterative process until you get to some point where, let's say, beta hat g is not much different from beta hat g minus 1. Okay. Now, with maximum likelihood estimation, we get some really nice qualities associated with our estimators. And that is, we have a way now to find what the covariance matrix is. Again, in a mathematical statistics course, you will learn about this, so I'm not going to go into details. But the covariance matrix for our estimates is simply that Hessian matrix inverted and then put a minus out in front of it. Okay? This basically represents, if you've heard of this term, the observed Fisher information matrix inverted. Again, R is going to automatically do this calculation for us, so you're not going to have to do any kind of by hand calculations, take the derivatives or anything like that. So this is what the form of the matrix then looks like written in terms of covariances and variances. So the 1, 1 element then would be the estimated variance of beta hat 1. The 1, 2 element is the estimated covariance for beta hat 1 and beta hat 2. This is the same form of a covariance matrix that you would see in a regression class as well. Just how we're finding this now is through using maximum likelihood estimation. Now, another nice quality or component of maximum likelihood estimation then is that, generally speaking, our maximum likelihood estimators, so if we think of the beta hat now as a random vector, has an approximate multivariate normal distribution where the mean is beta, what you're trying to estimate to begin with, and with that covariance matrix that I just represented. Actually proving that is way beyond what we do in our course here. Instead, in an asymptotics course for general maximum likelihood estimation as well, you would actually learn and go through the proof of the what's called often asymptotic normality of maximum likelihood estimators. In other words, maximum likelihood estimators have a large sample normal distribution. If you want to know more about it, here's a really good book on asymptotics. The book is called A Course on Large Sample Theory. Okay. So now that I know what the estimator, the distribution of the estimator itself, that allows me to understand variability and what I would expect this estimator to look like under certain conditions. Because of that, then that allows me to do inference. I can do hypothesis testing. I can do confidence intervals as well. So if I want to do a hypothesis test of, is a particular beta equal to some constant, beta 0, let's say, very often we will say, we will do this test to be more specific. Is my parameter of interest equal to 0 or not? Why is that important? Well, think of it, let's say, an AR1 model. If V1 is equal to 0, that says, well, I don't need that AR parameter at all. That's why we're interested in making these kinds of inferences. So to do this, we can do what's called a Wald test. A Wald statistic used in the Wald tests is this. Let's call it Z. And we just simply take our estimator, subtract off what the hypothesized value would be, and we divide by the square root of the estimated variance for that parameter estimator. In other words, people would put or call what's in the denominator here the standard error, SE for short. How do I find this square root of the estimated variance of that beta hat? Well, I just come up here and I find it from the corresponding diagonal element from my covariance matrix. Now, if the null hypothesis was true, then this Z, if I think of it as a random variable, has an approximate normal distribution to it. So what that means then, if let's say my type 1 error rate was 0.05, if I have a Z value that's outside of plus or minus 1.96, then that would say I have evidence against that null hypothesis. If, however, my Z value, my observed Z value is within inside of plus or minus 1.96, then that says, well, there's not sufficient evidence to indicate that the parameter is different from what is stated in the null hypothesis. Okay. Just a few more notes before we move on. Now, some time series textbooks perhaps go a little bit too far with some of their notation. They assume that students have had a PhD level asymptotics course, and so they will use certain notation that would correspond to that. So for example, in many time series textbooks, you will see the abbreviation AN. That stands for asymptotic normality with a particular mean, with a particular variance. You can just simply interpret that as your sample size gets large, I have an approximate normal distribution with that mean, that variance. Also, sometimes you'll see this notation represented, an arrow with a D on top of it. That means convergence and distribution. So using the result that I had before, we could say that beta hat minus beta converges in distribution to a normal random variable with mean vector 0 in this particular covariance matrix. If you see that in a corresponding textbook, just simply interpret that again as, for a large sample, beta hat minus beta has an approximate normal distribution as represented there. Okay, let's move on. So we're going to go back to that AR1 example that we've been working with in this course. Corresponding stuff I do here is in the file fit_ar1.r. Okay, so for this example, I'm just going to simply read in my data as I've done before. I'm going to put it into an object called AR1. I have a data frame that has two variables associated with it, t and x. And so I'm going to simply pull out the x and put it into a vector called x. I don't have to do that. It's just simple to do that just to make things look nicer, I guess. So how do I estimate my model using maximum likelihood estimation? Well, what I can do is I can use a function called ARIMA. The first argument is x, corresponds to where is my data? It's in x. Then the order argument says, well, what particular ARIMA model do I want to estimate? And so I combine together using the C function my value of P, my value of D, and my value of Q. I'm going to estimate an AR1 model because my data I know is simulated from an AR1 model. What method do I want to use for my estimation? The default is what's listed here, so I don't even need to put this as method. CSS-ML. What this means, it uses what's called conditional sums of squares to come up with initial estimates for our parameters, and then use those initial estimates then in my numerical iterative procedure to find the maximum likelihood estimates. This is the default. Again, you don't need to specify that at all. I just chose to do that here. And then lastly, what's also the default, but I put in here for emphasis, is include.mean equal true. What this is going to give me is my estimate for mu. Okay. Now, I'm going to put the results here into an object called mod.fit, meaning model fit. I could have called it something else if I wanted to. So let me go ahead and run some of this code in R. Now, unlike many R functions, there isn't a nice summary method function that will summarize what's inside of mod.fit. So instead, if I just type mod.fit, I get printed to my screen as follows. And let me actually come back here to Word so I can write on here. In my coefficients table then, I have my parameter estimates. Here is phi hat 1. Here is mu hat 1. I'm sorry, just mu hat. Down below we have what's called SE. That's my standard error. So this 0.0730 is the square root of the estimated variance of phi hat 1. Here this 0.3602 is the square root of the estimated variance of mu hat. 1.336 is sigma hat squared W in terms of our notation. Okay. Now, if I come back over here to 10, so what actually R is running here, go into some of the details, I guess, is R is actually running, in case you haven't seen this before, a print function by default. So if I say print mod.fit, I get exactly the same thing. Print is a generic function, R's terminology, and it goes then to a particular method function to run it. More about method functions later. Now, if I want to see more information about what's inside of mod.fit, mod.fit is actually a list. And inside the list, I have a number of different components. In particular, for example, one part of the component, or one component is COEF, or COEF. That stands for coefficients. And R uses that as a way to represent, here's where my parameter estimates are. I could also do mod.fit $sigma. Notice though that actually gives me my sigma squared, not sigma itself. So we can see up here, there's sigma hat squared. So this gives me my sigma hat squared. Oh, I'm sorry. I guess I could have also put sigma 2 there. That's what gives me my sigma hat squared. Now, why did R give me the exact same thing as if I would have put sigma 2 there? Is because what R is trying to do is match it up, and there is no other component to the list that has sigma there, so the closest component is sigma 2. Okay, if I want to get my estimated covariance matrix, I can do mod.fit $var.cof. There's my estimated covariance matrix, so that if I come back over here, this 1 diagonal elements, the estimated variance of phi hat 1. So if I were to take the square root of that, I get 0.0730. Okay. So let's do a hypothesis test, that Wald test for phi 1. So in other words, I want to know, is there sufficient evidence to indicate that phi 1 does not equal 0? If I can conclude that phi 1 does not equal 0, that says, hey, that sounds like a good thing to include phi 1 in our model. If, however, I say don't reject HO, phi 1 is equal to 0, that doesn't mean that phi 1 is equal to 0. Of course, in a hypothesis testing situation, you can never ever conclude the null hypothesis is true. Rather, what I can conclude is if I don't reject HO, that means there's not sufficient evidence to indicate that indeed phi 1 does not equal 0. It could be 0 or it might not be. So to do this test then, what I'm going to do is extract that first component in that coef vector. This is where that phi hat 1 was. And I'm going to extract the 1 element from my estimated covariance matrix. That's where I get my estimated variance of phi hat 1. And I'm going to take the square root of it. From that, I get 9.39. So just to emphasize all this, here is my vector of my parameter estimates. And if I just extract that first element, I get just that phi hat 1. Similarly, here is my estimated covariance matrix. If I were to extract the 1 element, in other words, row 1, column 1, this is what I get. So overall, we see that my test statistics 9.39. This is very large relative to a standard normal distribution. This is an unusual value to have if phi 1 was truly equal to 0. So because of that, I can say, well, reject HO. 9.39 is very unusual to have if HO was really true. If I want to find a p-value associated with this, I can use the p-norm function in R. P-norm stands for probability from a normal distribution. Now what the p-norm function actually finds is the area to the left of a value for a standard normal. What we actually want is an area to the right. Let me actually write that out to make sure that that's clear. So for a test like this, and whenever you're using a normal distribution like this with a two-tailed test, what I'm trying to find is as follows. I want to know how extreme my test statistic is. So let's say that I have a random variable A that has a standard normal distribution. I want to know what's the probability that A is greater than the absolute value of 9.39. Using an absolute value there because, let's say just in general, this test statistic could be positive or negative. This is my p-value. And I need to take 2 times it because it's a two-tailed test. So again, a measurement of how extreme my test statistic is relative to a standard normal. Well, I want to find then, if I were to draw out the standard normal distribution, centered at 0, I want to find this area that's on the extreme portion of my distribution. What R will find with the p-norm function is actually the area to the left underneath that curve. I want the area to the right. So what I'm going to do is take 1 minus what I get for the p-norm. The Q argument for p-norm, sorry I didn't mention this before, stands for the quantile. 9.39 is essentially a quantile that we're looking at. Standard normal, so mean equals 0, SD equal 1. So I find 1 minus the p-norm function and multiply it by 2, and I get a p-value that's extremely close to 0. So close, R just simply gives it as a 0. Okay. Now if I wanted to, instead I could also find 95% Wald confidence intervals associated with this as well. How am I finding this interval? I'm taking phi hat 1 plus or minus the value from the standard normal distribution, the 1 minus alpha divided by 2 quantile, times the square root of the estimated variance. And I'm writing over my normal distribution, so let me just move that. Square root of the estimated variance for phi hat 1. This is going to give me the confidence function, simply going to find this. And here it is for phi 1 itself, 0.54 to 0.828. So notice that 0 is not inside that interval. So this also gives me sufficient evidence to indicate that phi 1 does not equal to 0. Now the intercept here, this corresponds to mu. My interval is negative 1.13 to positive 0.27. Notice how 0 is inside that interval. So if I were to do a hypothesis test of is mu equal to 0 or not, I do not have sufficient evidence to reject. It could be 0. Then again, it might not be. Okay. So just to make sure this is clear, because I don't know if I mentioned this. So whenever we do inferences relative to maximum likelihood estimation, where we take the parameter estimate and we take that the estimated variance using maximum likelihood estimation methods. Whenever we do inferences like that, we're often doing what's called Wald-based inferences. Wald was a statistician from long ago. He's wrote a paper that examined this kind of stuff, and so that's why this is called a Wald test or a Wald confidence interval. Okay, so let's take a look at some notes here. So ARIMA estimates the model using maximum likelihood estimates. Here's what the actual estimated model looks like. So again, here's mu hat, there is phi hat 1, here is mu hat. So using what our true model would be, I just replace the parameters with their corresponding estimates, and this is what I get. Here is my whole alpha hat expression. Alpha hat, of course, is mu hat times 1 minus phi hat 1, since I only have an AR1 model there. Then you should always state, of course, then what sigma hat squared is as well. It's 1.336. So on a test, if I say, okay, or a project or some kind of assignment, if I ask you, estimate the model, this is how you need to write out the final result from the estimated model. It's not good enough just to say, okay, you can find what phi hat 1 is, you can find what mu hat is from looking at the output. You need to actually estimate the model and state it. So equivalently, we could rewrite the model like this so that I only have x of t on the left-hand side. Okay. Some other notes. We talked about this include.mean equal true. And that makes sense that if I have an argument called include.mean, and if I put true there, that means I want to estimate mu. What doesn't make sense, though, is that R's label is called intercept. Why is that? So let me just go back in the output. So there's where we see intercept. It would be nice if R labeled this as mu. Now what makes this confusing is that when I do rewrite my model like this, and think of it in terms of what we would see normally with a regression model. Beta 0 is the intercept parameter. And so you might be thinking, well, wait a second here. I should just put negative 0.4322, which is labeled in the output as intercept. I might just want to put that there instead of actually finding mu hat times 1 minus phi hat 1. That would be incorrect to put mu hat right there because that's not the intercept. It's used to find what we kind of think of as the intercept, but it's not the intercept itself. So be very, very careful. This is an easy mistake that can be made by putting what R says is the intercept as this portion of the model right there. Also, something to note is that R will not estimate mu, even if you put include.mean equal true in the ARIMA function call. R will not estimate mu if there is differencing in your model. So when you put order equal and then that second value in that vector, if you put d equal 1 or d equal 2, R will not estimate mu. And that makes sense relative to what we've seen previously, but there are still cases where you would want to estimate mu. We will talk about those cases later in the semester. Now there is another interesting way to estimate mu that's somewhat relative to what you might be what you should be used to seeing in a regression setting. And that is, we can include an argument in ARIMA called Xreg. So let's say that we use then the following to estimate our model. I put x equal x, order equal 1, 0, 0 for P, D, Q. Here's my method that I'm using to estimate. And now I'm going to say, okay, include.mean is equal to false. If I were to do that, R is not going to estimate mu. But now I'm going to include an additional argument called Xreg. And what Xreg is going to be equal to, I'm going to repeat a value of 1, the number of times of, in this case, 100, which is the length of x. I have a sample size of 100. So what that's going to do is as follows. I still get my phi hat 1, but look at this. I also get mu hat. Exactly what we had before. Sigma hat squared W is exactly as what we've had before. Well, what does this Xreg actually mean? Well, a way to think about it is as follows. In a regular regression class, if you were to write out your X matrix, often referred to as a design matrix that you use to find your beta hat vector, x prime x inverse x prime y, or I'm going to put lines underneath the corresponding matrices and vectors to emphasize that they should be bolded. So that's a standard thing that you learn about when you first learn about regression, how to find these parameter estimates for a regression model using matrix algebra. This X matrix looks like this. You have a leading column of 1s corresponding to your beta 0 term in your model. Then you have all of your values of your first explanatory variable or independent variable, then all the values of your second independent variable, and so on. That's what my X matrix looked like if I only had 2 variables of interest. And so basically what the ARIMA function allows us to do is essentially specify a matrix like this with the Xreg argument. In this particular case, I only specified a leading column of 1s using that repeat function, the REP function. This then allowed me to estimate mu. Okay, so we won't use this Xreg argument right now, but I just wanted to bring it up because we will look at this Xreg argument and we will need it in a later subsection of our notes. So don't worry about it right now. Now, if I were to find the sample mean of all my X values, I get negative 0.4963. Notice how close that is to what we get for mu hat. It's not exactly the same though, but it is close. So that's kind of reassuring that indeed we've done what we should be doing in terms of this ARIMA functions getting at the right place. Okay, so we've talked about that note. We've talked about our hypothesis test for phi1 as well. We've talked about how to use the confidence function to find confidence intervals as well. We've talked about how the iterative parameter or the iterative numerical estimation of the parameters works. What R actually ends up doing, if you look inside the inner workings of the ARIMA function, it actually calls a very useful function in R called optim. Optim is a very general function that can be used to maximize or minimize a particular mathematical function. I've used it a lot in my research itself, and ARIMA simply says, okay, I'm not going to reprogram in how to do maximum likelihood estimation here. I'm just simply going to send my likelihood function over to this function called optim and have that find the maximum likelihood estimates, and then it's going to come back to ARIMA, and then ARIMA is going to do some other stuff with it. The reason why I bring this up, and we're not going to have to use optim directly in this class, but the reason why I bring this up is because there are a number of different ways that you can control how the numerical iterative method works through using options that are available in optim, or arguments that are available in optim. And you can specify these arguments through the optim.control argument of ARIMA. You simply put these corresponding arguments into list. We really will not need to do this very often in our class, but it's good to know outside of this class that this option exists. One thing that might be interesting for us or useful for us is that we can specify a max it argument inside a list that allows the number of numerical iterations for us to use. So for example, since this is a numerical iterative method, you might not get convergence after the default number of iterations. And so the first thing that typically you do is increase the number of iterations to see if you can still get convergence. Okay. Now, ARIMA produces a list as its result where it stores all its information about how it did the calculations. And it also returns a class associated with this list. This class ends up being called ARIMA. In general, the function name doesn't have to match what the class name is, but in this case it does, or almost does. It actually uses a capital A here rather than a lowercase a. So that's the class of mod.fit. The reason why that's important is because then there are a number of method functions associated with that class. So for example, there's a method function called coef. So if I say coef mod.fit, coef is actually a generic function, and what ends up happening is that when that generic function's run, it looks at what the class is for mod.fit, and it says, oh, that class is ARIMA. So what actually ends up happening is that coef then sends it to a new function called coef.arima to actually run. Now, that did not work directly, and the reason being is because the users of R, I wish they wouldn't always do this. They didn't always do this in the past, but they know that no one's going to call coef.arima directly. Why would you call that method function directly when you can just simply use the generic function first? So because of that, it prevents you from actually calling it directly. But one way that you can actually call it directly is if you specify the exact package name where this function resides in, and I know it happens to be in the stats package. And if you do 3 colons to say, hey, look inside the stats package for a function called coef.arima and run that, then this is how it works. So anyway, let me come back over here. So we can see that we have a number of functions, method functions that are associated with this class. So there's coef.arima, there's log_like.arima, which gives you what is the maximum value of that log_likelihood function in the very end. There's vcov.arima as well. These names here, since you don't see .arima associated with them, these are actually the names of the generic functions. So if you say methods generic function equal vcov, and for some reason I printed it off twice there, here you can see the actual formal method function names. So for example, vcov.arima gives me my estimated covariance matrix, or I can just simply say vcov mod.fit and get it as well. Okay, so this little set of notes right here that I'm talking about here in terms of method functions, generic functions, I hope that this isn't new to you, because this is typically what students know before coming into this class, but I have found that sometimes that's not necessarily the case, so that's why I go over it here. Also, in my introduction to R for this particular course, I talk about method functions and generic functions relative to regular old regression analysis. And so if this is new to you, what I'm talking about right here, please go back and review my introduction to R notes and the corresponding videos. Now, one additional reason why I mention all this is that let's say you want to actually see how the calculations are being performed using these corresponding method functions. And if you say get anywhere vcov.arima, R is going to search through your packages to try to find vcov.arima and then actually print off what the actual function is. And this particular function is very simple. It's simply, okay, you're going to pass in an object, in our case was mod.fit, and then you're going to extract from that object var.coef. And remember, when we did mod.fit $var.coef, what did we get before? The estimated covariance matrix. So this just provides a different way to extract this, this information. Some people prefer just to use the generic functions. I prefer to actually look inside the object, find the component in the list, and then extract it that way. Okay, let's take a look at one more example. This deals with the ARIMA 111 example that we've seen previously. In this particular case, phi1 was 0.7, theta1 was 0.4, sigma squared w was 9, and we had a sample size of 200. Here's our data. Obviously, this is non-stationary in the mean. So let's try to estimate the corresponding model. So I'm going to read in my data as I've done before, put it into an object called ARIMA 111. Then I'm going to extract the x variable from that object and put that into x. Now I can estimate my model excuse me, using ARIMA. So I say ARIMA x equal x, my order of my model. Here's my P, here's my D, here's my Q. I'm going to use the defaults for the estimation method, also for include.mean, which in this case would be false since D is equal to 1. So then when I print off what's inside of mod.fit, or just to do the default printing method, excuse me, here's my phi hat 1, here's my theta hat 1, here's the square root of the estimated variance for theta hat 1, here's the square root of the estimated variance of phi hat 1. My sigma hat squared w is listed right here. And here is my covariance matrix. Here are my Wald confidence intervals. So I'm 95% confident that phi1 is between 0.5471 and 7969. Obviously, 0 is not within that interval, so therefore I do have sufficient evidence to indicate that indeed phi1 does not equal 0, which is what we would expect for this particular model, because we know that phi1 is actually 0.7. Similarly, for theta1, here's my 95% Wald confidence interval. Again, we have sufficient evidence to indicate that theta1 does not equal 0, which is what we would expect to happen. The default is a 95% interval, so I don't need to put level equal 0.95 there, but if I wanted to change it to something else, I could. We could then go ahead and do the corresponding Wald tests. I'll let you look at the details on your own because you're going to come up with the same answer. Notice the p-values are very small there. Okay, so some notes. We use ARIMA. No estimate of mu is found. I mentioned that before. Here's how I state my actual model. So again, if I say estimate an ARIMA 111 model, you need to go through this extra step of actually stating what the model is. So it's not good enough to only provide the output. So here's what the model would look like in terms of the parameter estimates in symbolic form. Then I replace the symbols with the actually corresponding numerical values. I could rewrite the model in terms of just having xt on the left side if I wanted to. Also, it's very important when you state your model, you do include this part right there. My estimated covariance matrix, we saw that as well. Here's a little bit more formality associated with the Wald test. Okay, some final notes for this particular section. We've talked about iterative methods don't necessarily always converge. First thing you should do is try a larger number of of iterations. Now, we've used normal distribution approximations here to find confidence intervals to do hypothesis tests. Another option that exists is to use what's called the bootstrap. Sometimes I talk about the bootstrap in our course. We would have a separate subsection on it. Sometimes I don't talk about it. But real briefly, what the bootstrap does, it allows you to get away from this normal distribution assumption and use essentially computer power to estimate a particular distribution for your statistic of interest. And then you can proceed with doing inferences. So with that then, that's the conclusion of this section on estimation.